All right, welcome to the most, yeah, the most powerful tool we're going to teach you in this course. Now, your Stokes equation in theory is the most powerful, but you really have to do a lot of work to make it useful. You have to program a solver for it, and then to actually solve realistic problems, you have to do all kinds of approximations. No, but Reynolds Transport Theorem is tremendously useful. The way it makes you think about a problem or a system is invaluable. It really is. Um, and so first we're going to talk about some vocab. Yeah, I guess full disclosure, I sometimes am on the fluid mechanics or the engineering students subreddits on Reddit, and like half the time there's a question about Reynolds Transport Theorem. It's about the definition of these two things. The first one is the system, and the second one is a control volume. And the difference between the two is this. Let's say we have a bunch of mass here. This is our system. It is literally everything we might care about. All right. And then within that system, we have a control volume. Okay. So a system is any well-defined amount of fluid. This could be the atmosphere. It could be a bathtub of water. In either case, it's in the sense that we say it's a well-defined amount of fluid. It's all the fluid we might care about in the course of a problem. So if we have something flowing, well, we'll get to this later. I'll try to make this clear later. It's hard without describing what a control volume is, so I'm going to do that next. Control volume is a volume of space that fluid can flow through. Specifically, fluid that is part of our system. Okay? So that should help, right? If fluid is going to flow through our control volume, it's part of our system, right? By definition, really, because we don't have to necessarily well define our system, but we do have to in the sense that we have to draw it or something like that. This is more of a mental construct, whereas this is a useful tool that we will draw and we will very well define on our problems. So our goal for this whole section, for Reynolds Transport Theorem, is to be able to apply conservation laws to fluid systems. So what conservation laws are there? Well, we have conservation of mass, conservation of momentum, energy. What else? Pizza? No, I'm kidding. I'm just hungry. Pizza's not conserved. You can eat it, right? And then it just disappears. Energy changes forms. Momentum is exchanged between force and momentum. Mass is conserved, period. There's no change in it. It doesn't change. It doesn't get converted into anything else unless we're talking about relativistic things here, but that's okay. We're not. So we really have three forms of conservation that we have to worry about in fluids. For the record, other people can use this tool too. Other engineers, for example, conservation of charge is useful for electrical engineers. Also, conservation of charge in chemical species can be useful for chemists as well, or chemical engineers as well. But let's jump right in and break it down. All right. So let's do a little bit more defining here first. Capital B is quantity we care about. And it is extrinsic. And extrinsic means that it depends on the amount of mass. So let's say we care about the amount of energy in a system. the temperature of an object times its heat capacity. What's that term? Heat times its specific heat times the amount of mass there tells us the amount of energy that is in that area, right? But if we wanted to worry about just the amount of mass per unit, just the amount of energy per unit mass, we would use the term lowercase b, which is uppercase b per unit mass. This is intrinsic and not dependent on amount of mass. So as a quick example, capital B, if B is equal to mass, so the amount, we're literally worried about the amount of mass. Lowercase b, I think you guys can probably figure this out. If we take mass and divide it by the amount of mass that we have, what do we get? We get 1. Right? So if capital B is equal to momentum, which is mass times velocity, if we have a little b, what's our little b going to be equal to? What is momentum, which is mass times velocity, divided by mass? Giving you a chance to write it down. And we have a velocity. It's a little bit harder. But if we have an energy, B is equal to energy. You'll notice, by the way, momentum has a direction, but energy and mass are scalars, so we did not add a vector to capital B. I should have added one to lowercase b. Lowercase b is going to be equal to 1/2 v squared plus however many different expressions for energy we want to add. This is the expression for kinetic energy per unit mass. We could also add potential energy, which is Gz, right? We could add pressure in there too if we really wanted to. There's ways to do that, right? And we'll talk about when we get to conservation of energy about how to do that. So, capital B is the quantity we care about. It's extrinsic. It depends on the amount of mass. And lowercase b is that same quantity but per unit mass. And it turns out we're not going to go through the derivation of this. I don't find it terribly useful. I'll be honest, I've never had students understand it when I did it in class. That's probably a fault of mine. But what we're going to do is we're going to take the material derivative. Remember that, right, from the last lecture. dt of some system quantity of B. All right. And it turns out this is equal to d dt, so the change in time, of an integral over our control volume of our density times our lowercase b, okay, integrated over the volume of our control volume. All right, we're going to come back to that, but we're going to continue on with this equation first. Plus, okay, the integral over our control surface, so just over the surface, of our density times lowercase b times the flux through that surface. Because remember, we're assuming that our velocity of our fluid is carrying stuff with it. So we have our b times the flux through the surface, which is given by the velocity dotted into n hat, which is the unit normal on the surface of the control volume. We'll talk about that, times dA, which is the area of the control volume. All right, so let's go back and talk first about this component here at the beginning. This part right here. So this part is the rate of change so the ddt of the amount of B in our CV. Because what we're doing is, remember, B is per unit mass. So if we multiply by the density, now we have a B per unit volume, but we're integrating over our volume. So that's a B times a volume, which gives us our total amount of capital B. I should have wrote capital B there. So it's the rate of change of capital B in our CV, our control volume. Okay? And remember, our control volume looks something like this, a box or a sphere or something that we're just drawing, right? So the rate, so the total derivative of capital B ddt is equal to the rate of change of the amount of B within our CV, and this is the rate at which B crosses our CV boundary. Okay, and this makes total sense actually if you just take a step back. Let's say you have a bucket, it's only open at the top. The rate of change of water in that bucket is going to be equal to the mass flux that passes through the open top of that bucket. So if you're pouring water in, the velocity of that water times the area times the density is going to give you the rate of the volume flow rate of the mass flow rate of that liquid entering the bucket, and that's going to be equal to the rate of change of water inside of the bucket. And it seems reductive to say it that way, but that's really all that this equation is saying. So remember, this lowercase b here is capital B per unit mass, which if we multiply by a mass per volume, cancels out there, so we get a B per volume. But then if we integrate over our volume, this is just equal to our total B. But again, we're taking the derivative, so this is the dB dt within our CV. Okay, and this is just our B times the density, again because B is per unit mass. So now we have a B per unit volume, so we have a B per mass times a mass per volume times, so mass cancel out, we have a B per volume, times a velocity times an area. We know what a velocity times an area is, right? Because remember, when you integrate, you end up multiplying by the d, whatever you're multiplying by, or whatever integrating over. So it's a velocity times an area. This is a volume flow rate. So what we end up getting here is a volume per time, which cancels out, and we get a B per time. So we have a B per time, a rate of change of B, a rate that B is crossing our boundary is equal to the rate of change of B within our container. Makes total sense. Okay. Now, the hard part comes in obviously applying this equation, because there are lots of little things that are important and tricky to understand. The first thing we're going to talk about is the dot product here, and we're going to work our way outward from this dot product in terms of things that we talk about. So the first thing is this unit normal of our control volume. Let's say we have this control volume over here on the right, and if I were to say N1 was equal to here, this is N1. Whoops, did I write that right? No. N hat 1. Let's say this is N hat 2. The one on the top is N hat 3, and the one on the bottom is N hat 4. If I asked you what the value for each of these things is, for N hat 1, it's extending in the positive y direction. I don't know why I wrote it this way, but I did. So n hat 1 is going to be equal to 1 y hat. N hat 2 is going to be equal to negative 1 y hat because it's pointing in the negative y direction. This is that right there, that difference between the negative and positive facing sides is probably the most confusing part about this whole entire thing. We have some tricks to make this easier so you don't always have to do the dot product, but it gets a little tricky thinking about which direction your control volume face. All right, so I'm going to let you do n hat 3 and n hat 4. Pause the video and write it, and then I'll write it. N hat 3 is going to be equal to 1 k hat, and n hat 4 is negative 1 k hat. Good. So that dot product means that our velocity, which is a vector, which has an x, y, and z component, is then dotted into the unit normal face for the control volume. And remember, what the dot product does is it takes the component of the two vectors that you're dotting that are parallel and multiplies them together. So if our one vector, our n hat, is a unit vector, has a magnitude of 1, always of 1, then if we are multiplying a unit vector, dotting a unit vector into a velocity vector, what we're really doing is we're taking the component of the velocity that is, this takes the component of velocity that is parallel to unit normal vector. And that's really important because what we care about is how much velocity is coming across our control volume faces, right? If the fluid is constantly traveling parallel to a control volume face and it's not entering or leaving, then it's not going to be taking any of lowercase b in with it. So we don't care about it. We want that to be 0 in our accounting because it's not taking b into or out of our control volume, so we do not care about it. So this takes the component of the velocity that is parallel to the unit normal vector. So we're going to stop this video after we finish this, after we finish writing this in terms of words, and then we're going to move on to talk about, in the next video, what happens if we set b equal to mass. Okay, so in words, the total derivative of b is equal to the rate of change of amount of b in our control volume plus the net rate that b crosses our boundaries. All right. So we're going to pause here, and then the next lecture video is going to talk about what happens if b, the thing that we're worried about so much, is mass.